Hi, good morning. Hope you can hear me and it stays this way. Sorry I couldn't be there in person, but this is almost as good and does have a lower carbon footprint. So today I am going to talk about the energy footprint of ML. And I'll start with a little bit of background. So for Google, sustainability really has been a core value since Larry and Sergey really founded the company. And in addition to the data center and server efficiency, we've done a lot of work on energy. So since 2007, we're carbon neutral. We did it with offsets at first, but then started buying renewable energy, financing new renewable energy installations. And in 2017, we reached 10 consecutive years of carbon neutrality, but more importantly, became the first major company to match 100% of our annual renewable, of our annual energy consumption with renewable energy. And then our goal became more ambitious, namely to become 100% carbon-free. And since this is relevant to the talk, let me briefly explain this concept. So let's look at our Chile data center just as an example. The status quo electric grid would give us to about 42% carbon-free electricity. So what you see here is an entire year. The x-axis is the year, the y-axis is the hours of the day. Green is good, black is bad, and so you can kind of see that you know there's some green energy, but not really that much. We didn't actually run the data center this way, but when we started construction of the data center, we also made a contract for constructing a solar farm. And so when the data center went live, the solar farm was live roughly the same time. So this is how it looked initially. So you can see during the day, we're pretty much carbon-free because solar farm is live. At night, there's still fossil energy. So after that, we later did a separate deal for a wind farm and for an additional solar farm with some storage. And so this is a forecast of how things will look later this year when both of these come online. So now you can see that we're on the order of 95, 96, maybe 97% carbon-free energy. And that means that directly on the local grid of this data center, 96, 97% of the electrons that we consume, so to speak, are from carbon-free sources in Chile. And because we match globally, over the whole year, everything, the whole rest is still carbon neutral, but it's matched by carbon-free energy that is produced somewhere else and consumed by someone else. We keep the renewable energy certificate. So that's what we mean by carbon-free energy. We have 5 of our data centers already today running at 90% or better our carbon-free energy, and so Chile would be number 6. So that brings us to the main topic of today. What about the carbon footprint and the energy footprint of ML? Is ML consumption threatening the planet? And it's understandable that there are these concerns. Here, for example, is a picture of a data center in Iowa, and it's not really a data center as in like here's a building with servers in it. It really is, a series of buildings with servers in them. It looks like a little bit like a small airport, and that's because cloud computing really concentrates the servers and the little data centers of lots of companies, lots of universities into a single place, and as a result, that place becomes and looks really big. It has a lot of energy usage, and so there's been an understandable interest in the carbon footprint of that, and there's been a lot of work. Some good and some not so accurate. So here's an example of some of the papers, and then here's an example of some of the headlines. These are pretty out there claims, $100 billion to train a single model. And so clearly people have forecasts, economic models, energy models that kind of converge towards infinity pretty quickly. And so in the rest of this talk, I will really walk you through some of the reasons why they are getting these numbers that are so ginormous, and why, in fact, the correct numbers are quite a bit small. So the reason why these predictions are actually so inaccurate is, of course, the assumptions that are behind the forecasts. And there's really two key misunderstandings behind, why most of these forecasts are really way off by orders of magnitudes. Those two key misunderstandings are, first, how neural architecture search works, and second, that they assume that the world is static when in fact it is anything but static. So first, let's talk about neural architecture search, or auto ML, as we call it. You're all familiar with it. Neural architecture search uses reinforcement learning to find better and better models for a particular problem. And to do that, it repeats a training run thousands of times using reinforcement learning to steer the search towards better and better models. And it works amazingly well. So here's the results for image recognition. You can see the blue line is AutoML 2017, a red line AutoML 2019, and then the dotted line is our hand-constructed models by experts. And then, same results also apply to language recognition. And generally speaking, what you can see is that you get higher accuracy at the same training cost, or lower cost for the same accuracy. So let's go back to the paper. The papers who reported these really high energy consumption numbers, they had really two misconceptions about AutoML. First, they assumed that the search itself is repeated every time we're creating a model, and meaning that each of these 10,000 or 20,000 training runs is really a full training run. And sorry, that's the second problem. The first one is really that this AutoML run is done every time you have a problem versus every time in a category, right? So in reality, these transform models, for example, they're trained once, they're created once, and then they're often published. But even if they're not published, they're reused hundreds or thousands or even 10,000s of times per domain space. And so the resulting model and the cost of that resulting model is really amortized over a very large number of use cases. And then the second use case, the second misconception of how about the search works. So the forecast assumed that AutoML works by repeating a full training model, a full training run, tens of thousands of times, and that obviously would use a lot of energy because it's 10,000 times more than a normal training run. But in reality, neural architecture search uses proxy models during the search, much smaller, much more efficient models. And so that makes the overall search much more efficient than with a full, if you repeated full training runs. So let's look at those headlines again. Thus creating one new transformer model really create as much carbon as 5 cars for an entire lifetime of a car. The answer, of course, is no. And really, it is a multiplication of those two errors. So the first error is really the overestimation of the training of the transformer itself. That was too high by a factor of 88 for this particular paper, partially because it ran on a more efficient hardware and actually used less carbon than assumed. And then that's a single training run. And then the proxy model misunderstanding is the other part. But then the bigger misunderstanding is really that this model is recreated every single time you use it versus just used as you start with a pre-trained model. And so in aggregate, those two multiply to a factor, really a staggering factor of 120,000 times. So instead of a 5 car lifetimes, it's really a tiny fraction of a single car lifetime, 120,000 times less carbon than assumed there. But actually, not only did those papers overestimate the impact at the time when they were published, they also, this energy usage actually has gone down since then, because today the carbon footprint would really be much smaller. Both algorithms and hardware have been improving rapidly. They're getting better every year. I'll refer you to the paper for details. I just want to highlight one thing here, namely that often people assume that the floating point operations that are done during training are a good proxy for the total energy used. And that actually used to be true 10, 15 years ago, but it's no longer true, because today it's really the memory accesses that drive energy. A single memory access uses significantly more energy than a hardware multiply. Since I'm a hardware guy, I wanted to mention that. Details are in the paper. And since I'm a hardware guy, I'll also show you some of that hardware. Here's a picture of Google's first custom-made chip for ML. In fact, these two were the racks. These two racks were the racks that were used for AlphaGo for the tournament against Lee Sedol. And because it was really specialized hardware that does ML and only ML, the energy efficiency of that chip was much better than the same generation CPUs or GPUs, right? So this is a chip that really only can do ML, in this case, inference, and as a result, really it's much more energy efficient. And since then, we've done more generations of hardware. See here, V2, V3, V4. And the one thing I want to point out, or really the two things, is that compared to previous generations, each chip has become much more performant and much more energy efficient. So for example, you can see V3 versus V4 is a factor of 3 faster. In a period of V4 versus V2, 3-4 years, you have a factor of 5 faster. And the most important innovation, of course, is that the cooling lines for the TPU V4 now come in Google color. So we're very proud of that. But let me end with a graph, of how this, with a picture of how they really look in real life. So they're not individual computers; they're linked together to into pods that also has a specialized network that really optimizes for training. So here's a graph of how this all adds up, this progress over time. In 2017, the transformer model was originally discovered, and 2 years later, there was Evolved Transformer. Another 2 years later, there was Primer, and actually Primer itself was 4 times faster than the original transformer. So we had an algorithm improvement. In that same time, the hardware that I just showed you became another factor of 14 faster. There's a data center efficiency I didn't talk about. It's in the paper that adds another factor of 1.4. And then the carbon per computation in a Google data center is actually 9 times lower than what the papers assumed. So altogether, you have a factor of 747 between the original assumption in 2017 and the actual state in 2021. So to summarize, there's really 3 reasons why these papers are off by so much, right? The first one is that we're not in a static world. Hardware is improving very rapidly. Actually, just was it this week or last week? NVIDIA announced their newest GPU, and is claiming that 6 times faster than what they released just 2 years ago. The algorithms themselves actually improve rapidly, and the algorithms themselves actually are more efficient than originally assumed. And then, of course, one thing I didn't have time to talk about is that the cloud data centers themselves are much more efficient than sort of your typical on-premise data center, and their energy mix is really trending towards fully renewable. Google itself has a goal by 2030 to really be carbon free, not just 100% renewable, which we already are today. And so this impact here really is going to zero, right? Not just 700 times lower, but to zero. Now, for this to be true, we all have to do our things. So let me end with a call to action. So first, cloud providers really need to enable these studies, need to publish their efficiency and carbon intensity per location, so that y'all can pick the right location and then understand what your carbon footprint is for your work. As practitioners, we of course need to use the most efficient hardware and the most efficient software. So make our computation important. Reducing the footprint is important. And then as researchers, we really need to put the energy efficiency, the energy consumption of ML training or inference as a goal function, right? As an attribute of our model at the same place, at the same rank as other attributes like accuracy or fairness. And so if we all do that, then I think in this aggregate, with this evolution, we will not only slow down the growth of the energy footprint or have it plateau. I think we will shrink it in the next 5 years or so. The paper has a few more examples that shows you the absolute footprint of Google as well. There's lots more detail in a paper, and I want to thank you for your attention. And during my Q&A, maybe we can leave up this QR code so people can download the paper if they have questions. So with that, thank you very much for your attention, and I'm happy to answer questions. Back to you, Marcel.
Thank you, Urs. Good. Very impressive. Thank you for all of these numbers and insights in obviously an absolutely critically important topic. So correspondingly, there are many questions coming in, and I'm even having a hard time sort of sorting them a little bit, but let me just start from the top and by ranking. One of the first questions that came in is about the calculation of the carbon costs and how that, what exactly was included. And the second most upvoted question is in the same spirit, right? Does the scope of carbon consumption calculation include only energy to run the computers in the data center, or also everything around the hardware manufacturing, employees driving around, and so on? So what's included?
Great question. So paper goes a little bit into the details. For those of you not familiar with carbon, it really comes in different scopes, quote unquote. So scope 1 is the actual thing. Scope 2 is sort of associated things like employee travel, etc. And then scope 3 is really the things that you import, the carbon you import from your manufacturing, for example, from other people. So this here focuses on scope 1 and scope 2, really the operational energy. So it assumes you have your gear, and the question really is, you're using it for this particular ML task. How much does this gear and really end-to-end with employees, with everything use? Scope 3 is not included, and it's an important thing. We didn't include it really for two reasons. One is the numbers themselves. The whole industry is actually not very accurate yet. So for example, if you say, what is the embedded energy of a disk drive or even a chip, you get lots of numbers. I think today those numbers are accurate to maybe within a factor of 1.5 or something like that. So you can measure them less well, and so we didn't want to put in inaccuracy. The second one is that this impact itself has to be dealt with as well and needs to go to zero. So as Google, for example, as a company, we're shooting for net zero, meaning that we want to make a scope 3 go to zero as well. This paper really just like the studies that were quoted, is only about scope 1 and scope 2, so it doesn't address that yet. My best guess, if you say next question, well, how big is scope 3 versus scope 1 plus 2, is that at least for Google, it's probably, I mean, and for data centers, it's probably somewhat larger, but not larger by an order of magnitude. So a factor of 2-ish larger than the operational energy is the embedded energy.
All right, thank you. So the next group of questions I would probably split into two, but they're all sort of in a similar spirit regarding transparency and open source. So I'm just going to read the first question here. What share of Google big models are in fact open source so that the training on the same problem does not have to be repeated?
I don't know. We use Transformer as an example. I think I linked to 2 or 3 in the paper. So we open source a lot and not 100% everything. The main, the goal of this paper was really to show that many of the frequently cited papers, really had misassumptions, underlying assumptions that weren't quite true, and to basically restate the numbers and explain how the restatement is different, right? I think if you actually have private models and only private reuse, I don't think it changes the conclusion that much, because you will reduce the reuse, but the reuse is probably still going to be in the hundreds of times, versus 10,000s of time, and 1 over x. Whether you divide a number that's not actually that large to start with by 100 or by 1,000 or by 10,000, you still end up with a pretty small number. Having said that, our philosophy is that in many of the broad places, and you've seen us do that in the last 5+ years, there is really a lot of open sourcing and a lot of publishing. So Transformer, for example, the example I mentioned, is open source, and a few other really big models by Google is. On the other hand, let's say, I believe OpenAI, GPT, 2 and 3 are not public, but at the same time, they allow reuse in different ways. So it's not just about open source, it's really about reuse by lots of practitioners.
Yep. Okay, and then I'm going to merge also a couple of questions into one, which is about the transparency of the energy consumed and all the research that you've done around this. Is that something that's public? That's going to be the first part of the question. And then the second one is sort of more broadly whether you think that any research paper using ML should essentially publish data on the energy consumption that's gone into the work.
Great question. To answer the second one, yes, absolutely. In fact, we asked for that in the paper. I think part of those misconceptions actually started because the original paper about neural architecture search did not actually include its own carbon estimate, and that was, it was actually a Google paper, so our fault. And that didn't allow other studies to discover this discrepancy in their assumptions. Our energy data itself is public. I believe there's a link in the paper. We publish it per location. We also have published our overall footprint for the last 10+ years, I think. We're part of the Carbon Disclosure Project, CDP. And so with some delay, every year we publish Google's overall, or actually Alphabet's overall carbon footprint, including scope 1, scope 2, and soon our estimate for scope 3. I think it's very important for that transparency to be there, because one way of reducing the carbon impact is to actually run your work in a region where the grid already is relatively green. There are huge differences in the world between, including in the Google world, between the lowest carbon intrinsically footprint and the highest carbon footprint. Net, this actually with Google doesn't, or with Google Cloud doesn't make a difference, because we compensate for any of the kilowatt hours that you consume locally that are not renewable by actually generating a matching kilowatt hour somewhere else or at a different time. So, and an annual sum, if we use X kilowatt hours of energy operationally in data centers, offices, we have X, fully 100% kilowatt hours of renewable carbon-free energy somewhere. But by placing your workload in the right region, you generate fewer gross emissions in the first place, and that of course is better than offsetting all of them. Even if you do that, 1-for-1 with renewable energy, not like some certificates, it's still better to not generate them in the first place. And so I'm really happy that we already have 5 regions that are 90% carbon free, across the year. And so that gives you a factor of 10 versus, or let's say a factor of 5 at least, versus sort of the average grid in Europe, in the US, in sort of many places.
Mm-hmm. Okay, so I'm just going to take the liberty to pose the last question myself, but I hope it's interesting to everyone. This is a bit more bigger picture question. I mean, there's obviously a lot of examples, and Google has been part of it, also that we see from others, where machine learning itself, of course, it's a source of energy consumption, but it's obviously also a way to find a more energy efficient way of doing things. Where do you think headed there? I mean, you can get views, right, from basically the whole spectrum, where basically people are saying, well, machine learning is polluting. I think you've shown good ways to avoid that. And then you get the other extreme, right, where people are saying machine learning will actually, somehow magically solve the climate crisis, which is obviously also an extreme view. Where do you fall on this spectrum? What do you see realistically happening in the next, decade or so?
Yeah, it's a very difficult question, because I think with all kinds of sort of technical interventions in nature, you really have to kind of define the box that you're measuring. And sometimes there are displacement effects or substitution effects or whatever that actually kind of offset the initial effect. But having said that, I think ML and actually IT overall, computers overall, have a very beneficial impact. If you look at, for example, actually data centers, we've applied ML to the control systems inside the data center. We've written about that publicly, and we have reduced the footprint, the cooling energy footprint of already like really heavily hand optimized buildings by another 30-40% through the applications of ML, on the controls. And generally speaking, a lot of industrial office and residential energy, and also consumer and consumer goods like cars, have control systems in them that work more efficiently with ML. So I think overall, I would be surprised if the carbon footprint, not just of ML, but actually of IT, meaning sort of enterprise computing, including industrial systems, etc., is negative, meaning it saves more energy in the processes that it controls than it consumes, for running those chips itself. But it's really a very it's hard to characterize ecosystems, entire processes, and get all the parts right. So this is a high-level estimate, not a proof. And I understand when people are skeptical about it, but if you just think about the opportunities of making physical processes more efficient, they could be chemical processes, they could be thermal processes, engines, etc. It is much more expensive to move a physical thing than to move an electron. And so generally speaking, spending computation to make a physical process more efficient is a net win, right? Because compute is actually relatively cheap compared to heating, for example. So I'm pretty optimistic that technology has, well, obviously contributed already, but can be a contributor to climate change. But it's a really difficult challenge, and there's no silver bullet, and technology is not that silver bullet either.
Yep, but can be a solution to the problem, part of the solution. All right. Well, we have to move on, and also, I mean, we were going to let you run, but thank you very much. It was a huge pleasure having you here, and this was a super interesting discussion. So, big round of applause, please, for Urs. Thank you, Urs.
Thank you. Thank you.
Bye bye.